The videos for the, is that the rest of them I did from at home. There's no class discussion or anything like that. Okay, so molality is moles of solute per kilogram of solvent. And as it says here, we can figure out the vapor pressure, how much it'll change the vapor pressure. Vapor pressure has to do with boiling point. So it'll affect the boiling point. We can use this to determine how much the boiling point will be changed or how much the freezing point will be changed. So that's the reason why we have this other kind. The first one we talked about works really good when I'm just mixing chemicals together. But this one doesn't work very good for that. So each one has a specialty. So molality is used because it doesn't change with changes in temperature. The other one changes with changes in temperature because it has to do with volume. If I warm up a liquid, what happens to its volume? It increases. You have that in your car. When your car engine warms up, all the water in the cooling system it gets larger, and it needs to have some place to go. So beside your radiator, you have this tank that the extra flows into while your engine is warm. And then the cap is a special kind of cap so that when your car engine cools off and it gets less, it sucks it back into the cooling system so it's always full. Okay. So unless you have other issues, your cooling system is always full. All you have to do is just check the tank. You never have to take the cap off or anything like that to check it. So the reason why for molality, it doesn't change with changes in temperature. Okay, so here are the two by comparison. The top one is molarity. Notice it's moles, and they're both in moles, but the top one is liters of solution. The bottom one is kilograms of solvent. So in other words, we're not trying to get to a certain number of kilograms. It's just I measure out my kilograms of solvent on the bottom one and my moles, and that's all I need to do to make them. I just put them together. Whatever it doesn't care. We don't care what the volume is. Okay, we don't care what the volume is. Okay, so let's apply that to these. Let's do these problems, and then we can maybe go back to the other one. Okay, a solution it was prepared by dissolving 17.1 grams of sucrose in 125 grams of water. Find the molar concentration of this solution. So we list our givens. They gave us the mass, which is 17 grams of sucrose. Remember the formula from last year? I don't know if you do. That was C12H22O11. And then we have the mass of the solvent, which is 125 grams of water. And we're going to find out the molality of that. So, what don't we have to use in our equation? What do we need? We need to have moles, right? So how do I change grams into moles? Okay, what we've been doing for chapters, we're going to have to find the molar mass of sugar. 12 carbons. See, carbons what? 12.01 times 12 would be, 12 times 12 is 144 plus, what is it, one?
Is it 144.12?
What, 144? It'd be 140, well, okay. Let's just approximate here. 144, 22 hydrogens would be how much?
22.
Probably around 22, right? A little, maybe 23. And 11 oxygens. That's a little harder to do. What's that?
167.
Flip the last two digits.
176.
Yeah, 176. Okay, add them all together, and we'll have this number right here, 342.34 grams is the molar mass of sucrose. So I'm going to use it as my conversion factor. So it has to be on the bottom. In other words, I have to divide. So that tells me that I have 0.0500. Remember, I have to have 3 significant figures. So I have 0.05 moles of sucrose. So it's not a lot of sucrose. Then, what's next? What's next? Are we ready to figure out the molality? What else do we need? Okay, we don't need volume on this one. Okay, I need to change the solvent mass into... don't look up there. Just look in your notes. What does the mass have to be in what units? Kilograms, right. Kilograms. So 125 grams is how many kilograms? How many grams in a kilogram? 1,000. Okay. I always like to find out more about, in Botswana, was everything a metric? Yeah, so you're having to learn about this English stuff? You know what I mean? Inches and feet and stuff like that. Yeah. If we were only all metric, it would have made it easier for you, and ultimately it'd make it easier for me. I know when I'm woodworking, like for instance on my CNC, it works much better if I just do everything in millimeters. If we're 3D printing, do everything in millimeters. It's just so much easier, but someday we'll change, but maybe not. Who knows? I don't know what it would take for us to change. We had a golden opportunity about 45 years ago, and we missed it. So we're going to change that, and that's why it's 0.125 kilograms. Now I think we have enough information to solve this. So I put my moles on the top and my kilograms on the bottom. So 0.05 divided by 0.125 is 0.4 molal. Kind of a hard word to sound, isn't it? Molal, or molal, as some people I think pronounce it that way too. Sounds almost easier to say it that way. So, any questions on how you solve that one? In chapter 13 is where we actually use this information to figure out, like how much is a boiling point raised, how much is a freezing point lowered, and stuff like that. Okay? Let's see. One more problem. Okay? Here we have a solution of iodine, and it dissolves in carbon tetrachloride. So if it dissolves in there, what does that tell us about the molecules? Or let's leave it at molecules. They're both molecules. If one dissolves in the other, what did you know about carbon tetrachloride from what we've already discovered in this chapter? Polar or nonpolar? Nonpolar. So if iodine dissolves in it, then it must be what? Nonpolar. Okay? Nonpolar dissolves in nonpolar, right? Now, iodine molecule, 2 atoms. Can it possibly have 2 opposite ends if they're both I's? If both sides are the same, can they be different? No, they have. So that's as pure nonpolar as you can get, that iodine molecule. Anyway, so that was just a little extra thing to tie together with things that we've already learned. Okay, it says it's used when iodine is needed for certain chemical tests. One thing that iodine is used for, but usually we don't mix it this way, we mix it with something else, is to test for starch. Like if we could want to find out if something has starch in it, we put a little bit of iodine on it, and if it turns purple, it does. If it just stays kind of a reddish brown, it doesn't. So that's kind of the test for iodine. Test for starch. How much iodine must be added to prepare a 0.48 mol solution of iodine in carbon tetrachloride if we have 100 grams of carbon tetrachloride? So we're going to list our givens. First thing they gave us was the molality of the solution we're trying to make of iodine, an iodine solution. They gave us the amount of solvent is 100 grams. So in this one, we already have it, the concentration. They want to know how much iodine must be added. They don't say that it has to be moles or grams, so we'll have to. So first thing we'll do is we'll convert the 100 grams of solvent into kilograms. So that's 0.1 kilograms. And then if we use our equation, we find out that, we put the 0.480 in where the molality goes. We put the 0.1 in the bottom where the kilograms of solvent goes. And now at the top, we can figure out the moles of iodine, which is going to be 0.0480 moles of iodine. What would you need to do if they wanted grams? What would I need to do? Yeah, I need to find the molar mass of iodine. That iodine we don't use very often, so I have to look that one up. And it's 126.9 doubled because it's iodine. It's an INE. It has to be a 2. So it'd be like 250, 60 something probably. If I needed to change it in grams. Or I guess it is 253. Okay, so this one isn't carried out to 2 places past the decimal like we usually do. I would still suggest that you do that. So you just keep it consistent, And so we need just 12 grams of iodine. 12 grams of iodine. Iodine is up there. Is it a solid, a liquid, or a gas, according to the periodic table? It's right there on the periodic table. Solid, liquid, or gas. What is it? What color is the symbol? Black, red, or blue? I think the other one. It's a black one. What does that mean? Yeah, if it's down here, if it's black, it says it's a solid. So it's a solid. It's how would you describe what the crystal looks like? It's really dark colored crystal, kind of like a really dark maroonish purple kind of thing, but it has kind of a silvery look to the crystal too on top of it all. It's kind of an odd looking stuff, but it's a solid. Okay, so any questions on that? Okay, so then let's go back to the third one that we didn't get to yesterday. Let's see, that would be, let's see if this is going to be that right. Okay, this is the one the bell rang on. So let's do this one. They gave us 40 grams of silver chromate, and we're to produce 40 grams of silver chromate, you need 23.4 grams of potassium chromate in a solution. And all you have in stock is a 5 milliliter bottle of 6 molar, and notice this is molar, not molal, potassium chromate. What volume of that solution do I need to get my 23.4 grams? Now, from what the problem is listed, is there an extra piece of information in this problem? Is there an extra piece of information? Do I need the 40 grams? No, I'm just saying, it's saying I need the 23.4 grams to make 40 grams, okay? So I don't need the 40. That's an extra piece of information in the problem, okay? So we have a solution volume, 5 liters, concentration, 6 moles, or 6 molar, and we're trying to get 23.4 grams of potassium chromate, and our product is that, but we think that's probably just an extra piece of information. So what volume do I need to measure out, how much liquid do I need to measure out so that in that liquid would be 23.4 grams? That's what I'm shooting for. And again, we didn't get to it.